in this, they want me to, figure out by partial sums how this sum to infinity formula comes about. We definitely have discussed it, but I'm going to go through it now, and especially when they'll use probably the phrase partial sums, and I wouldn't like that to throw you. It's really straightforward. It's just looking at it bit by bit in a general way, what we need to do. So think about it. If you have any sequence and you kind of, now we're talking about a geometric here, so this formula is only used for geometric. So what's the first term of any geometric sequence? We call it A. How do I get the second term? Like, what happens? Generally, we multiply by our common ratio. So the second term of a sequence is that. So this is it, just split up into its parts. Third term, fourth term, and so on. So my first term, I mean, if you want to hear it, you could put r to the power 0. I don't see the point in that, because any first term of a geometric to me is always called r. But maybe if you need to see the pattern here, so we can just write our last one. So the first one has an r to the power 0, the second one has an r to the power of 1, the third one has an r to the power 2, the fourth one has an r to the power 3. So the nth one is going to be that. Now, I hope that makes sense. I'm just going to scribble out this because it's not necessary, but it's just that you realise that this is a geometric, it's just a general way of writing a geometric sequence, and we don't know like what power we're going to, what term we're going as far as. So this is a sequence, a geometric sequence in its parts. So when they say partial sums, they're just saying, right, we're going to sum that up. So Sn is equal to A plus AR plus AR squared, because this just means I'm summing up my sequence, plus AR cubed plus ARn minus 1. So there it is in its partial sum. So I'm doing it for partial, showing you every part of what I'm doing here. Okay, so if we sum up our sequence now, we know that from our log tables, it's our first term, 1 minus my common ratio to the power of n, all over 1 minus my common ratio. And because we're summing to infinity, we're going to get the limit as n tends to infinity. Okay, I'm just writing it down for you so you can have a fair idea of exactly what we're looking at here. Now, I have asked you to think about this before. If you got any number and you put it to maybe the power of 5, picture what your answer would look like. Now put that same number to the power of 10. Picture what your answer would look like. Now put that same number to the power of 100, to the power of 1,000,000, and picture what your answer would look like. Most people, when they're doing this, will picture a whole number, maybe like the number 2, and they will put it to the power of 5. Oh, well, that's 32. And then they'll put it to the power of 10. I'll declare what that is. 1024. And they'll put it to the power of 50. Wow, huge, huge, huge number. What I'm going to ask you to do now is not to picture a whole number. I'd like you to picture a number between minus 1 and 1. So any fraction between minus 1 and 1. And we're going to say the common ratio is not 0, right? So we're going to leave out 0. So now I'd like you to picture any fraction. So let's say a half. And I want you to put that to the power of 5. Okay, so now we get a smaller number. Like, think about it. If you were to get a half of a pizza, well, what's 31 over 32 of a pizza? It's tiny. I wouldn't be happy with that. Or if we put that to the power of 10. Now we're at a really small number. You know, again, you could put it to the power of 50. You're going to end up with a tiny, tiny, tiny number. Eventually, if you put that to a really, 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 really high power, you'll head towards that this whole thing here is heading towards 0. So, you know, in the book, they like give a couple of examples, but I don't think I need to do that. I'm just going to say, as in for or, I'm just going to say that I'm putting or between minus 1 and 1. And when I do that, then or to the power of n, when you get the limit as n tends to infinity of this, you get pretty much 0. You get something so insignificantly small, it's heading towards 0. Now, what does that mean? Therefore, so you can write, therefore, if or is between minus 1 and 1, then as we approach infinity, the sum to infinity, what do we get? We get a 1 minus 0 all over 1 minus or. 1 minus 0 is 1. A times 1 is a all over 1 minus or. That's what we get. And that's my formula. So by partial sums, and if my common ratio is between minus 1 and 1, then we get our sum to infinity formula. That's a nice one, I think, about if they ask it.